This was electrochemistry, voltaic, electrical cell concepts combined, okay? So this was one from last week, and some keys here. A student uses a galvanic cell. Galvanic, voltaic, Luigi Galvani. These guys had an argument about a battery, so you know it's positive volts. They want to determine the concentration of ethanol. The whole purpose of this was to find the concentration of ethanol. What is concentration? I know that I've been doing this at home, but I want to give you an opportunity for me to do it live and in person. Okay, so what is concentration? Concentration deals with big M, which is called molarity or molar. And it's the amount of stuff dissolved. Mole is what we use of how much stuff. Now when we say mole of solute, that's the substance that gets dissolved. Aqueous ions go into the water because water can surround them, compete for the charges. So it's the amount of stuff dissolved divided by the liter of solution. You mix it with water, how much you have. So it's a ratio of stuff dissolved, particles, over the volume it's in. Okay, it's important. And so when I say concentration, I mean molarity or molar solution. Also, party people, you see brackets. For instance, copper plus 2. This means, what is the molarity of copper plus 2? Hey, Le Chatelier's principle. Increase copper plus 2, lower copper plus 2. Okay? All right. So in this problem, they give you the two half reactions from a standard reduction potential table that you did not have. The current way they do AP problems is they're going to give you these things that you need to use. No longer do they give you that table to look through. I give it to you for other problems to do to understand it. So you know you're making a voltaic cell. Given only these two reactions and knowing it's a battery, obviously, the only one you have to flip that would make it positive is this one. If you flip, okay, if you were to flip, if you flip this one, you're going to make it really, really negative. So the key here in understanding this question was the one that has to be oxidizing is the one that has to be positive. To get overall positive volts, you had to flip this chart, this sign. You had to go this way. It makes it positive. If you flip this one, it makes this negative. This big negative is bigger than that little negative, and the overall thing would be negative. That was the key to the problem, to understanding that you're dealing with positive volts. So, party people, you say, Mr. Grodsky, this looks really complicated now. Not really. Not really. Okay, yeah, they gave you the half reactions. You know you flipped the one. Okay, you turn this one around. Now you put them up, and you notice, hey, 12 electrons are being oxidized by the ethanol. Hey, and then what? 4 electrons are being reduced by the oxygen. We know that electrons have to what? Balance in a redox reaction. So I multiply by 3. 3 times 4 gives me the 12. 3, 12, and 6, 3 times 2. So essentially, by the distributive property, I have the numbers. And then we just cancel our hearts away. 12H pluses, 12H pluses. The waters are 6. This is 3, total 3. Obviously, electrons go bye-bye, and you should be able to handle this. Later in the year, we'll deal with redox reactions where we actually balance in acidic solutions. For those that finished the summer assignment, you saw that skill. We'll bring that skill back. Not right now. Okay? So, balance them. Hey, we don't multiply by 3. We put these together. Total volts. Pretty simple stuff so far. You should be able to handle that. Okay? Now, here's where we're using electrolytic concepts. Still the voltaic cell, but I'm using this idea of what? Charge. I'm using the idea of coulombs. I'm using the idea of moles of electrons to get what? What is the actual concentration? Here's the thing, party people. All right? I didn't draw it, but essentially at the anode, this oxidizes. Not the magnesium, this. And we're going to keep going until it what? Fully disappears. That's what completion is. We're going to keep running this battery to get 0 volts, which means this disappears. Okay? And so we measured how long that took. That took 20 seconds, and the voltaic cell produced an amp of 0.1. So what's the total coulombs? Kind of a silly question outside of what you want to do here, but they do this in AP chemistry. This is an AP chemistry pass question. I take my 20 seconds. I know that the amperage is what? 0.1 over a second. And what do I know? 2 coulombs of charge passed through the cell or the voltaic cell in that time period. That's all he wanted there. Here is the granddaddy of mol right here, or the grandmommy of all, grandmom, I don't know, whatever. Just trying to be politically correct, but it sounds awful. Okay, in any case. So, now I want the molarity. I want this for the ethanol. Assuming that that's how long it took, and that's the current that the battery produced till it ran out, went to completion, how many moles of ethanol was reacted? So I take the 2 coulombs, by the way, you could have put this right here, and I'm using my units. The coulombs balance off. I get total number of electrons by Faraday's constant. So ratio of charge for a mole of electrons. So now I have a how many number of electrons. And this is the key part. In the half reaction, maybe, in the half reaction, there is 12 electrons that are given off for every one. So that amperage, which is the charge per time, was created by the ethanol oxidizing. What is amperage? It's the charge of electrons traveling through the circuit. Who created it? This guy. So for every one of these, there's 12 of these. That's the ratio. Chemistry is about ratio of particles. So that's what I needed. You had to go back to your half reaction. So party people, if people want to go to the party, that's where I got the 12. Get rid of the electrons. I'm using my units. Get rid of the charge. There's one of these per these. So what do I have? A how many number of ethanol. Is it small? Yeah, who cares? It's the number. Don't be intimidated. Oh, it's really small, it can't be right. It's what it is. It's actually a huge number, isn't it? I mean, think about it. Because 1 mole is actually that big number. So even this small number means it's still a huge number, in truth. Okay, so this is my how many number of moles. Hey, I got that. I got the moles of the ethanol. What's molarity? Liter of solution. From the reading, they said they had 10 milliliters. Well, convert 10 milliliters to liters, and of course, that's a conversion that should be no problem at this point. And we get 0.01. Do your math. You get 1.7 times 10 to the 4, and that is your concentration, your molarity. So here's an example of a battery, and we're using the amperage in electrolytic cells, okay, and these kind of skills, and I'm combining them a little bit. Okay, I don't think amperage only occurs in electrolytic cells. No, there's an amperage in a battery. And don't think that magnesium or copper have to be the anode and cathode. No. In this battery right here, party people, Christmas, I'd probably have platinum sitting in solution. Platinum doesn't oxidize. This is what's oxidized at the platinum anode, and this is what reduces at the platinum cathode, right? Don't fall in love with it's always going to be exactly metal sitting in solution with the same ions. Okay, so let's go on to this one. Little straightforward question right here. Calculate the concentration of copper chloride that a tall teacher needs to provide for his students in electrolytic cell lab. Hey, we're doing one today. So the reaction, 1, 2, 3, 4, 5, 6, okay. We'll reach a completion in 20 minutes if the DC power source is kept at 2 amps. So this is like what I had to do for your lab. Hey, 20 minutes. What am I doing? Total seconds. I told you the amperage was 2. Amperage is coulombs per second. So I got total amps. I'm sorry, total coulombs. Faraday's constant. Total number of electrons. And what is this from? How do I know it's 1 to 2? Isn't copper chloride? -1 for the chlorine, -2 overall. The whole thing has to be 0. Copper is +2. How does copper +2 become copper 0 at the cathode? It must be gaining 2 electrons. Half reaction. And what's that give me? Now people that are robots and trying to memorize these problems would say, okay, what happened to the 64 grams equals 1 mole? I wasn't solving for how many grams of copper, I wanted just mole. So I wouldn't use that. Okay, so I got moles. Hey, top of molarity. What's the volume of solution? I must have told you that in there somewhere. But we're using 100 milliliters. And there's my molarity. So if I'm making a lab for you today, hint, hint, okay, I did this just to figure out, hey, I want to run the lab for a certain amount of time, what should I give them? These are the kind of calculations that I work. Okay, it's not exactly what's going to happen today, but you get the idea. Okay? So you should be able to handle a molarity question. Okay? It's still the same idea. Moles of substance, liter of solution. And of course these keys, and what? Some of these have lectures. All of this is given to you. Hopefully this is the first time you've seen it. People are writing, I'm like, maybe they want a fresh copy. Okay. Again, these keys are, I head on to today, so if you want to, have something cool to do today, you could go through these keys. These are all the keys of previous homeworks. Okay, let's go over the Saturday's homework, which is now going to give us a little more insight what's happening in our batteries for Lab 2 and Lab 1. Okay, so I don't know why I'm doing that thing, but I just feel like it felt good. Okay. All right. Now this was the demo. Christmas in July. I can do this. Okay. This is a demo I did over the weekend with a video. I could do it live today. It doesn't change anything. It's not that crazy. But what I'm doing is I'm adding a battery to a solution of water. And we're collecting hydrogen gas and oxygen gas, which is kind of cool in this demonstration. In the early 1800s, when this was done, they saw that they were making twice as much hydrogen gas as oxygen gas. They didn't know what to do with that until Avogadro's hypothesis much, much later. You have twice the volume, you've got twice the particles pushing on each other, right? Equal volume, same temperature and pressure, equal number of molecules. And why do we have twice as much H as O? Because water, of course, is H2O. So this was the first experiment that kind of told us what the formula of water was. But hey, wait a minute. They didn't write one. They didn't accept it. They didn't know anything about particles yet. They didn't know Avogadro's hypothesis. So it was just something that was just done. Hey, it's kind of cool. All right. But we're going to look at it from the perspective of, hey, why are gases being made here? Well, because there's oxidation and reduction of water. And by the way, these half reactions are in your net potential table if you need them. Okay, and I explained them this weekend. But we should understand that, hey, there's hydrogen. If hydrogen is being made, and notice in the problem given, okay, they give you the what? The standard net potentials. Look, I'm making hydrogen. So clearly that's a product. Clearly it's this reaction. Clearly it's as written, it's reduction. And that's why I wrote that. Look at the sign. What does that tell you? Does it happen naturally? Is there a pathway? No, you've got to add energy. Okay? The other one's making oxygen, which means the only place where there's oxygen is right here. So this one is going that way. Oh, like the sign. It's going that way. I like that. Now, if it's going that way, it's negative 1.23. Even needs a lot more energy. So what we're doing here is we're oxidizing water. Where would that be, the anode or the cathode? Anode. Here we're reducing water. That's, of course, on the red cathode. So those are the reactions. And guess what you need to do that? You need to know that a battery's making that happen. Now, don't think, well, he put this guy here, so that's got to go right there. No, I made you switch because I want you to think that it's not always going to be like a robot. This diagram connects to that. I want you to realize that, wait a minute. Between these two elements, chromium is more reactive, okay? It's the anode. The anode produces electrons here. This makes this negative. This is producing electrons. And it's forcing what? It's forcing the reduction. Here, these electrons are here to force water to get reduced. So at this electrode, we're making hydrogen. Hydrogen is being made, and of course, as written above, we've got the reduction. And there's your value, okay? So that occurs at the what? That occurs at the cathode, which is negative because it's connected to the negative part of the battery that pumps the negatives. Those negatives are forcing water to oxidize. And that's so beautiful to think why it occurs. What do we know about water? We know water, okay, has electrons that are tightly held. These are covalent bonds where they're sharing electrons. But water doesn't share electrons very, very equally. Because of the coulombic attraction that oxygen has for electrons, it pulls this pair closer. So these H's are electron deficient. And if you force electrons on them, they no longer are going to attract that oxygen, and it'll make hydrogen gas. Okay, so you're making hydrogen gas. And by the way, where else did we make hydrogen gas? Where else have we made hydrogen gas in any lab? Lab 1 and probably Lab 2, but Lab 1, the magnesium was forcing its electrons onto the hydrogen of water. What were we doing in Lab 1? We were reducing water. But what do you think was happening on the other side? Possibly oxidizing water. These reactions always occur, okay, in aqueous solutions. These are another errors that pop up, hello, in Lab 2. Okay? So, any case, you have to balance them. We times by 2 because electrons aren't balanced. And then what we have? Water breaking apart into 2 H's and 1, 2 to 1. And you get some of this stuff here. Okay? And total net potential is negative. Why is it negative? We go to the beach. Who doesn't like the beach? This is West Hampton Beach. We go to the beach. Do we see a cavern? Oh, there's a nice continental shelf that goes down into the Marianas Trench. Okay? You don't see those things. Why? Because water is stable. Water hangs out. It stays in our cells. Does water break down into hydrogen and oxygen normally? No! You've got to add tremendous energy to make water break down, which means it stays around. Okay, now this is important because we'll see this as a cool demonstration later on. Because water doesn't like to be reduced or oxidized, you've got to give energy to break it apart. It's terrible at breaking apart, which means really what? Really good coming together. When these guys come together, they explode. Batteries can explode. Aqueous solution batteries. Hey, this is a fuel cell. Fill a car with some water, have some electricity, put some electrodes, you have exactly the ratios you need, and you can actually move a car by a fuel cell. Okay? By the way, liquid hydrogen gas, liquid hydrogen and liquid oxygen, which became the gas, are the fuels that push the space shuttles into orbit. That main fuel tank was liquid hydrogen and oxygen. Why was it so much energy given off? Because it's really, really good making water, which means it's really, really bad breaking apart. These are things I hope you can pick up. All right, so the challenging part of this lab, or this question, was be able to figure out who is the anode of the battery first. And then, of course, it makes this the cathode. How did you know this is the cathode? Because reduction had to occur for H2. You had to break that down. Your quiz, just like your last, Thursday's form, is based upon this. I'm putting it all together, but now I'm adding this little layer of water being oxidized and reduced. Anytime you've got aqueous solutions and charges, okay, remember the Ki, potassium and iodine demonstration I did in class? We're making iodine and we're fizzing at the other. What was I also making? Hydrogen and oxygen, fizzing too. Okay, in truth. All right, anytime I got an aqueous solution, all right, moving on. And then, of course, you have the questions that you should be able to handle there. Okay, so moving on. One more, I think. Did I do that one? That one? That one? That one? Okay, let's talk about lab. All right. So, lab 2, implications of electrolysis of water. I don't know if you quite get this, but I want to make sure you see it because people get confused and don't see this normally. If I take my battery, and again, I'm being cool and I want to be edgy. I've never been edgy in my life. All right. Maybe a neck tattoo would do it. All right. Of a squirrel. No, that wouldn't work. Okay, so take a battery. Make this the anode. Positive cathode for the millionth time. Let's flip it. So now I got this battery with the anode here, it's negative, and the cathode, it's positive. Let's make this bigger. Extend this. Hey, if it's negative here, it's still negative here, right? Hey, if it's positive here, it's still positive here. Hey, put this in a solution, what do you have? Electrolytic cell. That's why it's negative. Okay? And of course, if I have water, if this is the anode, this must be the what? Cathode. Reduction occurs. What gas am I making here in water in an aqueous solution? Hydrogen. Bubbles. You're forcing electrons onto the electron deficient H's. We're making here oxygen because its cathode is the anode. Well, guess what? Those things are also occurring inside the cell, okay, at each one if there's enough energy present. And that's also a competing reaction, not just the oxidation, not just the reduction of water. So something to think about there. All right, now let's go to lab 2 because a lot of people in lab 2 do not know how to explain some of the errors, okay? And there's some things that I expected you to know and some things that you didn't know. So I want to give you some hints for lab 2. Lab 2 is not due yet, okay? And, okay, so I'm going to give you my possible solutions. If you don't like what I say here, you can actually just read what I'm going to say here. If I hit the view, these are my notes of what I did. So I competed against you. It just so happens I won. So I get the breakfast. Just kidding. Okay, no, we don't want that. Hopefully we have enough. Here we go. So let's do this. Hopefully it works. Okay, so let's talk about what I use to do this, all right? So, how I set this up, and I just go over my thinking, and in my thinking of how I did lab 2, I'm now bringing in our ideas of oxidizing and reducing water, and also the ideas of Le Chatelier's principle and the limitations I had. So you only had some things to pick from. So here's my idea. Okay, I think our top voltage was 0.8, and I think it was in this class. All right. Now, here's what I chose. I chose aluminum, and I chose copper. Now, here's my overall reaction. Aluminum 0 plus copper plus 2 goes to aluminum plus 3 plus copper 0. I need to balance it. I would need 3 here and 2 here. And that would make the charge the same on both sides. Okay, so given all of that, okay, what did I start with? Well, I started this with nothing. I had no solution here. Okay, and I used KOH. Now I have NaOH written there, but it's really K plus and OH minus. It wouldn't change anything. And here I had copper plus 2, really blue solution. Okay, why did I choose aluminum? Okay. Oh, I'm sorry, what's that? Okay, yeah, it's the most reactive. Of all the metals, it's the most reactive. Now I know there's an issue, just like magnesium, there's an issue. I knew that aluminum, so good at losing electrons that I was betting, and I knew this was going to be a limitation, that it was also going to force the reduction of water to make what gas? Right. I was forcing the reduction, okay, of water. I was making water get reduced. Now, anytime oxidation reduction occurs in one spot of a half cell, it's not occurring in the other spot. Remember, we're trying to separate oxidation here and reduction here to get to what? Flow of charge, to have some amperage and a voltage and a force. If I make the oxidation reduction occur here, then I'm not doing it across the wire and I'm limiting the amperage and a voltage, correct? So that was an issue, that I know that I was going to make hydrogen gas because I know that water was going to be reduced, as if this was an electrolytic cell. You have to think, not just voltaic cell, we don't do, no, we're forcing water to get reduced. We're pushing electrons onto water. And the better that this oxidizes, the better as a what? Reducing agent. It forces reduction to occur. Yes, this is the anode, but if I'm having what? Reduction occur here, aren't I limiting the oxidation? Absolutely, okay? We don't want reduction, but I know that picking aluminum, it was a balance. The next chemical that was the most reactive was zinc. So it would react less with water, but it had less voltage. My guess was having higher, a better, a more reactive metal by a lot even with it reacting water, would still give me more volts. So I went with it, even though there was some limitations. Okay. Now, starting with no water, all I wanted the salt bridge to do was fill it up. The salt bridge water would push some solution in here, correct? And my thinking was, by having so some people put what? Aluminum nitrate in here. Why would you start with aluminum nitrate? Because you're a robot. Aluminum goes with the same ion. Keep this low. Le Chatelier's principle. If I lower this concentration, molarity, isn't the reaction going to shift more forward? So my thinking was, do not put any aluminum plus 3 in here. Limit it. So I started with nothing, okay? And I let the water flow in, okay? And I don't know how well that worked. But it starts to flow in at some point. Solution starting to flow, and it eventually works. And right now I lost. Now, what I'm going to do is, as it's oxidizing, there's aluminum plus 3 starting to build up. So I know there's a limitation there. So next thing I'm going to do is pour water. Okay? In fact, the best way to think about it, if I do this again, start with this pure water. Pure water means I start with the lowest amount of aluminum plus 3. Okay? So at some point, I'm going to pour pure water in there. I'm just trying to see if, I'm trying to win. Okay? Okay, stop. Pour the water in already. There we go. So now I'm just having pure water. And give it a second. You can see the voltage climbing. And why? I'm limiting aluminum plus 3. Okay, so that's one of my shifts. And adding pure water is, of course, going to dilute the aluminum concentration. The reaction will shift forward and I'll produce higher voltage there. So I had an increase by doing that. Of course, it's going to die as more aluminum plus 3 is. Now, here I'm adding more copper chloride or copper sulfate, whatever I'm doing, increasing the copper plus 2 solution. And of course, increasing the copper plus 2 solution, the reaction wants to do what? Decrease it by Le Chatelier's principle, and that also will push it more spontaneously by the forward direction. And that gave me a little bump here. And then the greatest amount of bump, now here I am adding more water, so I'm trying to dilute the aluminum ion concentration even more, okay? But I'm kind of losing that battle because aluminum's oxidizing. So, this is something where, this is NaOH, I snuck it in there. It's actually KOH, it's the same thing, I'm adding hydroxide ions. And you can see by adding hydroxide ions, I added more of the solution of the hydroxide, I got a bump in my voltage. This is about 1 right here, this is 1.5. All right, so I'm already class winner, all right? So it's, yes, I know, it's all about me. Okay, but I'll go second place, it's a even less modest lunch. Now I'm adding more solid KOH, even though I say NOH. And by adding more OH minus to here, what I'm doing is I'm adding more of the chemical that's going to take away the oxide layer that's keeping aluminum from reacting, okay? And so if you look carefully, you're going to see a tremendous amount of fizzing here, as we know that aluminum, keeping it exposed to the oxygen, is making more hydrogen gas. So that fizzing is the reduction of water into now what? A hydrogen gas, because by the increased amount of hydroxide reacting with the oxide layer, I'm exposing more aluminum. Yes, I'm losing some of the voltage, but that was something I was willing to do. Now I kind of played with this and tried to heat it, because remember, something else to talk about lab 2, just like lab 1, the voltages you expect are based upon standard conditions. 0 of cell, 25 degrees Celsius, 1 atmosphere pressure, and 1 molar solutions. I'm trying to heat it to see if it does anything. It didn't do much, okay? And I also tried cooling it, all right? But the last thing I want to talk about is some people pick this system. And I don't know what we're going to do here, but the next system is some people try to use iron plus 3. I'm trying to cool it now, all right? And some people, I'm not cool enough. Okay. All right, so the last little system maybe, oh, here we go, is people got low voltage with this system, or they got negative voltage when they tried iron plus 3. So iron plus 3 didn't react very well as expected. Now there's a couple different things, and again, you can read my little blurb, but iron plus 3, this is something that I wouldn't expect you to know, okay? And it's okay to get the lab quote wrong and not get a positive or have the wrong voltage as expected. This is where you learn, okay? Iron plus 3, actually, here's the fizzing going on, and the reason why I'm getting a voltage where people didn't is I'm making aluminum what? I'm exposing the aluminum to the water and to the voltaic cell by having that hydroxide ion there. But a lot of people didn't have the hydroxide here, got negative voltage in this cell, and I want to explain that, okay? So the reason why, and this is something you should be writing, and we're going to learn about this, the reason why that this system didn't work well for you, and again, in real life, you guys would have been able to do trial and error a little bit in this lab. You didn't get a chance, but let's think about iron plus 3. If it's plus 3, is it highly charged based on Coulomb's law? High charges equal higher force of attraction, correct? And if I lose 3 electrons, become plus 3, which iron does, right? Iron 0 loses 3 electrons to become iron plus 3. The more electrons you lose, the smaller you get. Why? Because the proton number feels bigger, and it pulls in electrons more and more, and we'll learn that. So this plus 3 for iron is pretty small, and it's highly charged. So it's got a small radius and high charges. Coulombically, by Coulomb's law, it attracts things. So in water, water gets pulled in. It gets pulled in so much that only 6 waters can surround it. Now I'm drawing a 2-dimensional drawing, but this would be 3-dimensional. Now I'm drawing only 5, but only 6 surround it. And it would look like this. We would draw this as a complex. We call this a complex ion because we actually get 6 waters that stick together, not just a random amount of waters. We draw like this, Fe with 6 water molecules. The whole complex is still plus 3 because each water has no charge. Now, I know I have 5, but I can't fit, the other one may be at the top. In any case, let's take these away right here, make a bigger water. These are actually electrons. Now, because of the Coulombic attraction, that plus 3 in a small area, high charge density, these pair of electrons drift toward the what? Plus 3. So if these electrons drift even more, the H comes off without any electrons. And by the way, that's called a proton, and that makes an acidic solution. And what do we know in your reference table? H pluses plus an electron give you H0. Specifically, 2 H pluses, 2 electrons gives me H2 gas. Okay? So party people, we're making an acidic solution. If I've got an acidic solution, that acid can react with the metal. And that acid reacts with the metal to make what? Hydrogen gas. Redox occurs here. If the H plus is available in high concentration, what's it going to do to that metal? It's going to pull electrons. And you're going to have oxidation and reduction. In what? You're going to have oxidation reduction when you're supposed to have just reduction only. If you've got oxidation reduction occurring here, where you want the what? The reduction to pull the charge through. If you're passing electrons here, it's not going to pull charge. So the reason why this solution didn't work the way you thought is because of the acid that was produced, the H plus that was produced, because this ion actually is very acidic. You are adding H pluses in solution. This, if you look at your standard reduction table, is a pretty strong oxidizing agent. With most metals, it'll pull electrons away to make hydrogen gas. So if you have a complete oxidation reduction reaction occurring here, there's less of the pull across, right? What's the point of a battery? Keep the reduction over here. Keep the oxidation over here. Make this push the electrons here. Make this pull. If there's a transfer occurring right in the solution, it doesn't care about this. Path of least resistance is right here, and that limited your battery, okay? All right, enough of that.